Hi, hey, welcome to 9-7. This is the last lesson in Chapter 9, our first chapter about quadratics. And 9-7 is a bit of a wrap-up, and it's about applications of quadratics and why quadratics are important. Read through the chapter. These really are quadratic equations describe an awful lot in the world and get used in a lot of different ways. So it's important to review that, understand it, and maybe recognize when you have a problem in your future for one of your classes or in your work that perhaps a quadratic equation is an appropriate way to evaluate the situation. Well, let's get through to some examples. First one up is pretty common quadratic one, although this is not exactly a parabola. We approximate a curve like this as a parabola. Most people would tell you when they look at it that it is a parabola, but it's in fact what's called a catenary. And a catenary differs from a parabola in that since there are suspension ropes, which you can see here in the picture, they pull on the curve in slightly different ways. It's not just a function of gravity, the way that it loads up. And so it changes it a little bit. For our purposes and for many purposes, treating it as though it is a parabola works just fine, and you can get awfully close to what you need. If you were actually making a bridge, you would make no assumptions, and you'd be doing very exact calculations to build this. Let's take a look at the question. Building this bridge at 300 feet and at 800 feet, excuse me, at 0 feet and at 800 feet, the cable is at 300 feet high. Halfway in between those, it's at 0 feet, and halfway between 0 and 800 is 400. So let the bridge be along the x-axis. The y-axis is one end of the bridge, which is at 0, 0. Because the parabola is symmetric to the line, x equals 400, the parabola passes through the points 0, 300, right there, 400, 0, right there, and 800, 300 here. You can use quadratic regression. This is found in your Inspire calculator. You're not going to need to do it, but it's useful to understand how you can input the points and do a regression calculation to get an equation for regression. See me in class if you'd like some help with how to do that. In standard form, the equation we would get is this one: y equals 3 over 1600 times x squared minus 3 halves times x plus 300, which tells us that when x is 0, y is 300, y is the length of each vertical cable at the distance x from the end of the roadway. So basically, as we go any distance, it's the height between x-axis and where we intersect the larger cable. Suppose two support cables of length 200 feet long are delivered to the construction site. How far from the left end of the bridge should the engineers place the cable? Well, if we were to draw a graph of this and draw a line for y equals 200, we'd see that indeed it would cross this catenary, our parabola, at two different spots. Well, we can use the information from this calculation to figure out where those spots are. So the length is 200, so it's x is whatever it is and y is 200. So we have that 200. Hang on, let me change colors here. There we go. 200 equals, 200 is the y value, right? 3 times 1600 x squared minus 3 halves times x plus 300. There we go. We've got our quadratic equation. Now, in order to solve it, we would like to use the quadratic formula, so we have to set it equal to 0. That means we will subtract 200 from both sides of the equation. Doing that, I have that 0 equals 3 over 1600 x squared minus 3 halves x plus 300 minus 200 is 100. Now I've got something I can calculate. First thing I would like to see is, using the discriminant, how many solutions I would have. I believe I'm going to have 2. It's useful to know this because if it's impossible, I'd like to know that right away. If it is possible, I need to know what b squared minus 4ac is anyway. So I'm going to find discriminant. And so I get that b squared is a negative 3 halves squared minus 4 times AC, and that's 4 times 1600 times 100. Oops, one too many zero there. And I can get rid of a couple of zeros because 100, these zeros will cancel out, right? Because 100 will go into 1600 16 times and goes into 100 one time. So these will cancel out and I'm left with 3/16. This is 9/4. 4 goes into 16 4 times. Right? So 4 goes in. So that would be minus 3/4. And that's going to equal 3 from 9 is 6. Will be 6/4. So I get that b squared, or the, okay, got that the discriminant is 6/4. So that's going to be the square root of 6/4. The square root of 6 over 4 is equal to the square root of 6 over 2, right? Because 4 is 2 times 2. Okay. Now what I'd like to do is take this square root of 6 over 2 and put it into the quadratic equation. So let's go ahead and do that. I'm going to have the opposite of b, and b was negative 3 halves, so the opposite would be 3 halves. So I'm going to have 3 halves plus or minus the square root of 6 over 2. This whole thing over 2 times a, which was 3 over 1600. Okay, so let's do a little bit of simplification here, just to, especially this term in the denominator. I know 2 will go into 1600 800 times, right? And these are both over 2, although I'm not sure I want to do anything with that just yet. Let's see, 3 halves plus or minus the square root of 6 over 2, all of that over 3 over 800. Okay, now I'm going to multiply, I'm going to invert and multiply everything up here, so I'm going to have 800 times 3 plus 800 times the square root of 6, and this is over 2 times 3, this is over 2 times 3. 3's cancel here, 2 goes into 800, I get 400. That's plus or minus, right? Plus or minus. And it's interesting, 400 is our midpoint, right? 800 times root 6 over 2 times 3. Well, 2 goes into 800 400 times. So this is 400 times the square root of 6, all of that over 3. So now I'm ready to do a calculation and get my approximation, because I would like to know a distance, and if I tell somebody it's the root of something away, that doesn't help them much. So I need a reasonable approximation of distance. I'm going to go ahead and put that in, and we'll do our calculation. So I get 400 plus 400 times square root of 6 divided by 3. And that tells me that in adding this, I'm at about 727 feet. Or, when I subtract it, so 400 minus, or 73 feet. Okay, so we've, looks like we've got an answer. Let's get back to our problem here, and 200 feet long, how far from the left end of the bridge should the engineers place the cables? So we've got our two answers. Now, equally true, we could have plugged this equation, that the quadratic, into our calculator, get a graph of the parabola, compare it to the y equals equation for y equals 200, and see where our two intersections are along the graph. Do you want to see that? Okay, hang on a second. Okay, we got our calculator up and running. We'll go ahead and put in our function for this. This is the y is 3 over 1600 x squared, so I get, put it in parentheses, 3 divided by 1600, close parentheses, times x squared. That's going to be minus 3 divided by 2 times x, and that's then plus 300. And go ahead and hit enter, and there we don't have our graph. Well, we got to get our window right. So let's get our window settings in here. -10 ought to work. For x minimum, I'll make it 850. For x max, and might as well be symmetric. We'll make this a -10 for our y minimum, and for y max we'll go with 350. This is kind of arbitrary. I just wanted to be above what I'm looking for, but not so far that I can't see it. So let's see what we get. And okay, we can get a pretty decent view of the graph. And what we want to do now is to plug in our next function, and that's going to be f of 2 of x equals 200. Enter that. I've got it, and I want to look for intersections now and see what intersections I have. Remember, I got to put boundaries on it, and I have one at 73.4. and another one at 727. Well, so 73.4, 727, how does that compare to our calculations? Well, a little bit. 727 is good. A little off on the 73. I'm not sure what we did there, or what I did, but I think giving our approximation, that's probably good enough. Okay, let's get on to the next example, and this will be the last one for this chapter. This one, example 2, the formula S equals n squared can be used to find the sum of the first n odd natural numbers. So what are natural numbers? You need to know that to begin to see. So for n is 1, for our n value, if it's 1, 2, 3, then it equals the sum of the first n odd natural numbers. So for 1 squared, it's just 1. So 1 plus 0 is 1, or there's only one natural number? I don't know. So this is our S. For 2, for n is 2, 2 squared is 4. Okay. For 3, 3 squared is 9. So let's look at what this is. This is probably 1 plus 0, so that's just 1. Taking these, what am I going to do to get 4? The second odd number, so it must be 3. So 1 plus 3 is 4. And 1 plus 3 plus 5 is 9. So 1 plus 3 plus 5 plus 7 is 16. So 1 plus 3 plus 5 plus 7 is 16, and 4 squared is 16. So we get it that these are our first odd natural numbers. So what is the sum of the first 20 odd natural numbers? Is simply S equals 20 squared, and that's equal to 400. And then the next question that it asks is, can the sum of the first n odd natural numbers be 230? If so, how many odd numbers are being added? If not, explain why. Okay, so this is asking us for, let me grab something here. So this is saying, can 230 equals n squared? And if so, how many odd numbers are being added? If not, explain why. So we would need to solve this. We could use the quadratic formula for it, but we don't really need it. We just need the square root of both sides. So the square root of 230 is equal to the square root of n squared. And this is plus or minus, but I don't care about the negative values. I'm only interested in positive values. So I only want the positive root of 230. Let's find out what that is. So square root 230 equals, so this is approximately 15.17 is approximately equal to n. And what this tells us is that, can the sum of the first n odd natural numbers be 230? And the answer is no, because n is not an integer, and n would have to be an integer solution in order for this to be true. That's it for this lesson. Get ready for the chapter test, and good luck on wrapping this up. See you in class.